Hello everyone. In the previous video, we studied about the Zener diode and its application as a voltage regulator. In this video, we are going to study about the rectifiers, the different kinds of rectifiers, and also we are going to study its efficiency and the ripple factor. Let's begin with that. So, what is a rectifier? Before going into the rectifier, I can say rectifiers are nothing but the application of PN junction diodes. That is, application of a diode is nothing but a rectifier. Now, what is this rectifier all about? A rectifier is a circuit which is going to convert the AC input, whether my input could be in terms of voltage or it could be in terms of current. It is going to convert this AC input into DC input, DC voltage or current. So rectifier is a circuit which converts AC input voltage or current into DC output voltage or current, and the process that we call it as a rectification. These rectifiers are broadly classified into two types. One is half-wave rectifier and the other one is full-wave rectifier. Again, this full-wave rectifier is classified into two types. One is center tap rectifier and the other one is a bridge rectifier. In the half-wave, let us move on for the half-wave rectifier. The name itself suggests it is going to have or it is going to convert only for the half wave. Let us consider a transformer where the AC input is given for the primary winding of the circuit, and at the secondary winding I can expect the voltage, input voltage, that is Vs. Now, during the positive half cycle of the input, so during the positive half cycle of the input, I can say the polarities at the secondary winding of the transformer will be positive and negative. Now, with these polarities, I can say my diode is now in the forward bias condition. Since it is in the forward bias condition, I can say my diode is going to conduct and there is a flow of current. Now, I can say my AC input voltage is now getting converted into DC for the first positive half cycle. Now let me go for the next negative half cycle. During the negative half cycle, the polarities at the secondary winding of the transformer is going to be negative and positive. Now when you look into the polarities of the secondary winding of the transformer, I can say my diode is now in the reverse bias condition. Once it is in the reverse bias condition, I can say my diode is now acting as a open switch and there will be no flow of current. As a result, there is no conversion of AC into DC. So as a result, I can say my output waveform is going to be 0. There is no conversion of AC into DC waveform. So in my half-wave rectifier, I can say during the positive half cycle, the diode is forward biased and it acts as a closed circuit, and during the negative half cycle the diode is reverse biased and acts as a open circuit. As a result, no current flows through it. Now after studying this, now let us study the average or DC current that is going to be present, or the let us calculate the average or DC current that is going to get converted whenever we apply the AC input. Now looking into the waveform, I can say for the first, that is uh, for the for one cycle of the input, that is one cycle means it is going to vary from 0 to 2 pi. For the one full cycle, I can say during the positive half cycle I can expect the output, whether it could be in terms of voltage or whether it could be in terms of input, it is going to get converted into DC. But when we go for the negative output voltage, negative input voltage, I can say my output is 0, whether it could be in terms of current or whether it could be in terms of voltage. Now looking into this waveform, let us derive the expression for AC average DC current. Okay. Now when we look into this, we know our IDC is given by IDC is equal to integral from 0 to 2 pi divided by I naught into d omega t. I naught into d omega t. Now you might ask me why this average current. Average current is given by the expression as average current is equal to area under one cycle of output current divided by the time period of the output current. So what is your average current states? It states that the area under one cycle of output current divided by the time period of the current. So area under one cycle of output current is I naught or IL into d omega t, and the time period is, it is going to 2 pi. So 1 by 2 pi integral of 0 to 2 pi IL sin omega IL into d omega t, where my IL is nothing but my Im sin omega t into d omega t. When we integrate it and when we split the limits, we know from 0 to pi we have the conversion from AC to DC, and from pi to 2 pi we don't have the output conversion. So as a result, we cannot apply the limits, it becomes 0. So as a result, my IDC would be equal to 1 by 2 pi integral of 0 to pi Im sin omega t into d omega t, where minus Im by 2 pi into cos omega t pi, apply the limits. So my IDC, total IDC current, that is average DC current, average or DC current for the half wave rectifier is given by IDC is equal to Im by pi. Now once after knowing the average DC current, let us go for DC voltage. We know our VDC is equal to IDC into RL. Now we know what is our IDC. Substitute Im by pi into RL. Right? IDC is Im by pi. Substitute RL. What is my Im now? What is my Im? Im is given by, I can write my Im is given by Vm by RL, or the total resistances. My RL and RL is going to get cancelled. Now as a result, my VDC would be equal to Vm by pi. Now after knowing the DC average or DC current, let us go for deriving the RMS value of the load current. RMS value is nothing but, the square of area under. IRMS is given by the square of area under one cycle of output current divided by time period of the output current. Now IRMS is equal to square root of 1 by 2 pi integral from 0 to 2. 2 pi. When you split the limits, we know pi to 2 pi doesn't have any waveform. So as a result, substitute it for 0 to pi. Im squared into sine squared omega t into d omega t. Now what is this? I can substitute my sine squared omega t as 1 minus cos 2 omega t by 2. Substitute it, apply the integral and apply the limits such that my IRMS value would be equal to Im by 2. Calculate the VRMS, where VRMS is equal to IRMS into RL. Substitute, we know IRMS is Im by 2 and we know Im as Vm by RL. So it is nothing but my VRMS would be equal to Vm by 2. Now let us go for calculating the next parameter, that is nothing but my power conversion efficiency. That is, we are speaking about the efficiency. Now let us calculate the efficiency, which is defined as the ratio of DC power, that is, we can see ratio of DC power delivered to the load to the AC power supplied from the secondary of the transformer. The name itself suggests efficiency is nothing but DC power delivered to the load divided by AC power supplied from the secondary of the transformer. So PDC divided by PAC, where my power efficiency, conversion efficiency is given by eta. Now let us calculate what is this PDC and PAC. PDC is nothing but I squared into DC into RL, where I square DC, what is my IDC for half wave rectifier? We know it is Im by pi. Since it is a square, substitute I squared m by pi squared into RL. Now what is my PAC? PAC is nothing but, it is nothing but an IRMS square. So it is IRMS squared into the total resistance is substituted. So this is nothing but I squared RM. So when we come for the efficiency, I can say the efficiency of the half wave rectifier, when we calculate, it is nothing but 40.5%. So where it says that out of 100% of AC power input supply, it is going to convert only 40% of it. Rest of the thing is going to be the negative half cycle is not going to get converted into DC. As a result, I can say out of 100% of AC input, only 40.5% of it is getting converted into DC. Now, once we convert this, now let us go for the calculation of A's ripple factor. Now, what is a ripple factor? Ripple factor is the ratio of RMS value of the AC component present in the rectified output to the DC component at the rectified output. That is, it says that ripple factor is nothing but it is the amount of AC component present in the DC output that we are getting. Now, we have told rectifier is going to convert AC into DC, but we are not saying that it is not directly converting it into pure DC, right? So in order to get converted into pure DC, we use other forms. We'll look in the next coming videos, but as of now, it is going to convert into DC, where it is going to have some AC component, which we call it as ripples, and we are going to measure that ripple in terms of what is a factor. So it is represented by gamma. Gamma is equal to VAC divided by VDC, which is nothing but given by square root of VRMS divided by VDC whole squared minus 1. Substitute. we know Vrms, we know Vdc. When we substitute, we get our ripple factor as equal to 1.21, which gives an inference that 1.21% of AC component is present in the converted DC output by a half wave rectifier, right? So this is about the ripple factor. Now, regulation. When we go for the regulation, it is nothing but a measure of how well the rectifier is able to maintain a constant output voltage between no load and full load conditions. We have seen in the Zener diode load and no load conditions. So regulation is nothing but it is maintaining the constant output voltage whenever you apply the load or no load in the no load and no load conditions. So for the half wave rectifier, the percentage of regulation is given by Vm by pi minus IDC into RL, IDC by IDC into RL into 100%. Now make RF and RL as equal to approximately equal to 0. So your percentage of regulation is given by RF by RL into 100%. This is about the half wave rectifier and its parameters, that is about the ripple factor, efficiency, its average DC or average or DC current. Hope this video is useful to you. Thank you.